You solve AX equals B and found one answer. But in many systems, there are infinitely many more solutions, forming an entire geometric surface through higher dimensional space. Every solution fits a single elegant formula. One particular solution plus every vector in the null space. That formula is our target. Let's build it with a specific system. Here's our system. A is a 3x4 matrix. Row 1, 1, 2, 2, 2. Row 2, 2, 4, 6, 8. Row 3, 3, 6, 8, 10. The vector B is 1, 5, 6. Now let's form the augmented matrix and row reduce. First, subtract 2 times row 1 from row 2. So we get 0, 0, 2, 4 with augmented entry 3. Next, subtract 3 times row 1 from row 3. We also get 0, 0, 2, 4 with augmented entry 3. Notice both rows turned out the same. Now subtract row 2 from row 3. It vanishes completely, giving all zeros. The echelon form has pivots in columns 1 and 3. Those correspond to pivot variables. x1 and x3, columns 2 and 4, have no pivots. So x2 and x4 are free variables. A free variable can take any value, and the freedom is exactly what creates multiple solutions. Step 1, find one particular solution. The recipe is to set every free variable to 0. So x2 equals 0 and x4 equals 0. Now the system simplifies. Row 2 of the echelon form says 2x3 equals 3. Divide both sides by 2 and we get x3 equals 3 halves. Circle that result. Now move up to row 1. Row 1 says x1 plus 2, x2 plus 2, x3 plus 2, x4 equals 1. With x2 and x4 both set to 0, this becomes x1 plus 2 times 0 plus 2 times 3 halves plus 2 times 0 equals 1. That simplifies to x1 plus 3 equals 1. So x1 equals negative 2. Circle that result as well, putting it all together. The particular solution is xp equals the vector negative 2, 0, 3 halves, 0. We picked the laziest option. Every free variable gets 0. This is a convention for simplicity, not a requirement. Any choice of the free variables would give a valid particular solution, but 0 is the easiest. Step 2, bring in the null space, the set of all vectors x, where a times x equals 0. We find basis vectors using the same free variable method, but now with b set to 0 on the right-hand side. For the first null space vector, set the free variable x2 equal to 1 and x4 equal to 0. From the second echelon equation, x3 plus 2 times 0 equals 0, so x3 equals 0. From the first echelon equation, x1 plus 2 times 1 minus 2 times 0 equals 0, giving x1 equals negative 2. This gives us x as 1 equals negative 2, 1, 0, 0. For the second null space vector, set x2 equal to 0 and x4 equal to 1. From the second equation, x3 plus 2 times 1 equals 0, so x3 equals negative 2. From the first equation, x1 plus 2 times 0 minus 2 times 1 equals 0, so x1 equals 2. This gives us x as 2 equals 2, 0, negative 2, 1. Notice that these two vectors are linearly independent. You can see this because x as 1 has a 1 in the second position and 0 in the fourth, while x as 2 has 0 in the second position and 1 in the fourth. The general null space vector is c1 times x as 1 plus c2 times x as 2. Now we can assemble the complete solution. X equals the particular solution, xp plus c1 times x as 1 plus c2 times x as 2. Written out explicitly, that is negative 2, 0, 3 halves, 0, plus c1 times negative 2, 1, 0, 0, plus c2 times 2, 0, negative 2, 1. Here, c1 and c2 are arbitrary real numbers, and as they range over all values, this expression generates every solution to the original system. We need to confirm that this formula captures every solution, no more, no less. This is a two-part proof. First, the forward direction. we show that everything the formula produces is actually a solution. Multiply a by xp plus c, 1 times xs, 1 plus c, 2 times xs, 2. By linearity of matrix multiplication, that equals a times xp plus c, 1 times a times xs, 1 plus c, 2 times a times xs, 2. Now a times xp equals b because xp is a particular solution. Times xs1 equals 0 because xs1 is in the null space. And a times xs2 equals 0 because xs2 is in the null space. So the whole expression simplifies to b plus 0, which is just b. Every vector the formula produces is indeed a valid solution. Check. Now the reverse direction, we show that any solution must be captured by the formula. Take any solution x satisfying ax equals b, compute a times the quantity x minus xp. By linearity, that equals ax minus axp, which is b minus b, which equals 0. So the vector x minus xp lies in the null space of A. Since the null space is spanned by xs1 and xs2, we can write x minus xp as c1 times xs1 plus c2 times xs2. Therefore, x equals xp plus a null space vector, which means x has the form given by our formula. Check. Both directions are confirmed. The formula generates exactly the complete solution set, all solutions and only solutions. Here's the geometric picture. In 3 dimensions, suppose the null space of A is a line through the origin. Solutions to AX equals 0 live along that line. Now shift that entire line by the vector x particular. You get a parallel line, same direction, but passing through x particular instead of the origin. And that shifted line is the complete solution set of ax equals b. Let's draw a dashed arrow from the origin to x particular to show this shift. This object is called an affine subspace or a flat. It has the same shape and dimension as the null space, just translated away from the origin. Same direction, same dimension, just translated. Now let's summarize. The null space is a line through the origin. It's a subspace. The solution set is a parallel line through x particular. It's an affine subspace, also called a flat. In our actual problem, we had 2 free variables, which means the null space is a 2-dimensional plane through the origin in R4. The solution set to ax equals b is a parallel plane shifted to pass through x particular. So the dimension of the solution set equals the number of free variables, which is 2 in our example, giving us a 2-dimensional flat in R4. 2 common confusions to clear up. First, the particular solution is not unique. Any solution to ax equals b works as xp. For instance, if you set x2 equal to 1 instead of 0, while keeping x4 equal to 0, you get a different particular solution. But this new xp prime is just the original xp plus xs1, giving us the vector -4, 1, 3/2, 0. This makes perfect sense. xp solves a, x equals b with x2 equal to 0, and xs1 solves ax equals 0 with x2 equal to 1. Adding them gives a solution to ax equals b with x2 equal to 1. The key point is that the affine subspace stays identical. It's just a different description of the same set. Second confusion, is the solution set a subspace? The answer is no, unless b equals the 0 vector. Here's why. Check the 0 vector. Times the 0 vector equals the 0 vector, which is not equal to b when b is non-zero. So 0 is not in the solution set, and it fails the most basic subspace test. The solution set is an affine subspace, sometimes called a flat, but it is not a subspace. Let's step back and see the big picture. The formula x equals xp plus xn encodes 2 independent questions. The first question is about existence. Does a particular solution even exist? It does only when b lies in the column space of A. If b is not in the column space, then no solution exists. The system is inconsistent. The second question is about uniqueness. Is the null space of A just a zero vector? That happens when every column is a pivot column, meaning there are no free variables. A trivial null space means exactly one solution. A non-trivial null space means infinitely many solutions, with the dimension of the solution set equal to the number of free variables. So to summarize, the column space governs existence, and the null space governs uniqueness. Here is the big picture captured in one formula: x equals x particular plus x null space of A. Right? One particular answer gives you a foothold. It is any single solution to ax equals b. The null space gives you every direction you can move without changing ax. In other words, every vector in the null space of A satisfies ax equals 0. Together, x particular plus the null space of A captures every solution in a single elegant formula. This structure extends far beyond systems of equations. It applies to least squares problems, differential equations, and any linear problem you will encounter. Master this decomposition, and you hold the key to all of them. Coming up next, column space, row space, and the 4 fundamental subspaces.